Predicting project defects is a critical risk management task due to its direct impact on project quality, cost, timeline, and reputation. Monte Carlo simulation can handle defect rate uncertainties by modeling them as non-continuous probability distributions. In this video, we'll create and share a dynamic template in Excel with 3 easy steps: simulating project data with non-continuous distributions, running multiple iterations and plotting histograms and S-curves, and calculating p-values and percentiles. You can follow along by getting the Excel workbook by the provided link in the description below. Step 1 is simulating project data with non-continuous distributions. Our case study focuses on a residential development project with 4 activities. Foundation has an estimated defect rate of 4 per project, but our previous projects show that there is a probability and randomness around this activity. In such scenarios, Monte Carlo simulation can be a useful computational technique which relies on repeated random sampling to estimate the probabilistic outcomes. The best discrete distribution which explains defect variability in the foundation is binomial distribution. Goodness of fit tests such as chi-square show how well a probability distribution fits historical data, which are defect counts in our example. To simulate foundation defects, activate Excel's Data Analysis Toolpack via File tab, Options, Excel Add-ins, and Analysis Toolpack. Once activated, go to the Data tab, select Data Analysis, and choose Random Number Generation. We can specify 1 variable and 5,000 random numbers for binomial distribution. The p-value of 4% over 100 trials aligns with our estimated defect rate of 4 per project. We can specify the output range by clicking on the appropriate cell, and Excel will generate 5,000 random numbers for us. The summary statistics at the bottom of the spreadsheet with an average of almost 4 validate the alignment with the observed data. For a quick browse of this large spreadsheet, use Ctrl key plus down arrow to visit the last row. You can use the Ctrl key plus up arrow to return to the top. You might have noticed that simulated foundation defects range between 0 to 13. Let's enter this array in our spreadsheet to generate beans for our histogram. To animate our non-deterministic data and draw professional histograms, navigate to Data tab and Data Analysis. From the list, choose Histogram and press OK. For input range, we should select Simulated Defect Counts for foundation. Click on the first couple of rows and adjust the range in the dialog box to include 5,000 rows. For bin range, select the array which we specified earlier. Remember to check 2 tick boxes for cumulative percentage and chart output. By clicking OK, the histogram is created in a new sheet. You can adjust the size and remove unwanted elements to make it ready for project risk and quality management reports. Visual inspection of our non-continuous variable and histogram hump shows the most probable number of defects. It would be possible to find different p-values by drawing 2 perpendicular lines as demonstrated for P80 here. The second activity of concrete pouring and curing has a single point estimate of 4 defects per project, and the best fitting distribution to historical data is Poisson distribution. We can generate random simulated inputs by navigating to Data Analysis and choosing Random Number Generation. We can specify 1 variable and 5,000 random numbers for Poisson distribution with lambda equal to 4. We can specify the output range by clicking on the appropriate cell, and Excel will generate 5,000 non-continuous inputs for us. The third project activity is related to a structure, and its defect status is binary. Historical data from our previous projects show that a structure might be faulty in 20% of the time and healthy in the remaining 80%. For modeling this situation, the best fitting distribution is Bernoulli. We can specify 1 variable, 5,000 random numbers, and the probability parameter or p of 20%. Please note the binary status for defect rates, which means we have only 0 and 1 in the mix. In larger projects where structural integrity is critical, a multiplier can be applied to assign a higher weight to structural defects. This adjustment introduces a mean shift in the total number of defects for the project, which reflects the increased impact of structural issues on the overall risk assessment. The fourth project activity relates to interior works and has a complex probability pattern. Our historical project trends in this array show the probability of having 0 to 12 defects. The best fitting distribution based on this complex pattern is discrete. To simulate this in Excel, we must define a single variable and generate 5,000 random numbers. For discrete distribution, specify the value and probability of input range by clicking and dragging across the respective array on the spreadsheet. We can animate our non-deterministic data and draw professional histograms by following the same procedure shown for the binomial distribution. Histograms for our 4 input distributions allow the visual inspection of project quality data and sanity checks before running 5,000 iterations in the next step. If you want to simulate continuous variables such as time and cost in Excel, the video links are provided in the description below. Step 2 is running multiple iterations and plotting histograms and S-curves. Let's start by calculating the total project effects for the set of 4 activities. Click on the relevant cell and press the equal sign. Use the sum function in Excel to add up non-deterministic defect estimates of 4 activities defined by their statistical distributions. Next, we should hover the mouse on the bottom right corner of the cell where the fill handle is visible. Double-click the plus sign to automatically generate 5,000 non-deterministic predictions for total project effects based on the data range. This large dataset of defect predictions helps mitigate the impact of outliers or extreme cases and allows a reliable analysis of total project effects. To animate results of 5,000 simulation iterations and draw professional histograms, navigate to the Data tab and select Data Analysis. From the list, choose Histogram and press OK. For the input range, we should select Project Total Defects. Click on the first couple of rows and adjust the range in the dialog box to include 5,000 rows. For bin range, we may select a suitable array based on our output range. Remember to check the 2 tick boxes for cumulative percentage and chart output. By clicking OK, the chart is created in a new sheet. You can adjust the size and customize the chart for your project quality and risk management reports. The histogram is similar to the probability density function or PDF, and the S-curve is similar to the cumulative density function or CDF. To analyze confidence levels and confidence intervals, it would be possible to find different p-values by drawing 2 perpendicular lines as demonstrated for P90 here. Step 3 is calculating p-values and percentiles. We can now focus on the quantitative calculation of percentiles using our tabular data. Let's start by calculating the 50th percentile or median or P50. Click on the relevant cell and press the equal sign. In the formula bar, enter percentile.exe or exclude and select the output array. Click on the first couple of rows and adjust the range in the formula to include 5,000 rows. The next function argument to enter is the kth percentile, which is 0.5 or 50% here. We can follow the same procedure for P80 or 80th percentile, P90, P95, P99, and P99.9. The comparison of p-values shows the increasing defect predictions when confidence intervals increase. The beauty of this risk analysis technique in Excel is simplicity and creating preliminary results and inferences. However, it's important to note that Excel produces pseudo-random numbers, not true random numbers. These are generated using a deterministic algorithm that relies on a seed value. While they may appear random, they are predictable based on the seed and the algorithm employed. Excel is useful in implementing scenario and sensitivity analysis, plotting tornado charts, as well as worst case and best case evaluations, which are valuable for data-driven decision-making in project management. For more advanced project risk assessments, it's recommended to use ISO 31000 and specialized software such as Oracle Primavera Risk Analysis, Palisade at Risk or Lumivero, or Crystal Ball to achieve greater precision and reliability. And there you have it, an easy and short implementation of Monte Carlo simulation for non-continuous decision variables using only 3 simple steps in Microsoft Excel. If you found this video useful, please remember to like and consider subscribing. I look forward to reading your comments and seeing you in the next one.